Hello and welcome to lecture 14. We're going to cover, in the first half of this lecture, we're going to cover the later sections of chapter 21 from Survey 11th edition. And then in the second half of this lecture, we're going to get into chapter 22. What this lecture represents is the introduction to light. We're going to be talking about light for the next few lectures, and this is the first lecture, where we're going to be getting into it. Our objectives are to learn insight into how electromagnetic waves were theorized by Maxwell and experimentally supported by Hertz. We're going to see how to calculate the speed of light, understand the concept of light intensity and the momentum possessed by light, and become acquainted with the electromagnetic spectrum. Okay, so let's get into some key terms first. Okay, so our first key term is Maxwell's Law. And so Maxwell's Laws. So Maxwell's Laws are the underlying laws of all of optics, electromagnetism, and circuits. So they're kind of a big deal. So all of optics, electromagnetism, and circuits. In a sense, of course, circuits falls under electromagnetism if we're talking about sort of Venn diagrams, right? But these are kind of topics that are often discussed, so it's important to know that all of them are explained by Maxwell's laws. I'm not going to present Maxwell's laws. They are differential equations, partial differential equations that are outside of the scope of this class, but we want to understand them conceptually. And as far as these three topics, the one that we obviously have not discussed yet is optics, and that is going to be the topic of the next few chapters and the next 5 or 6 lectures. Okay. What I will say about Maxwell's laws is that, among other things, they state that a changing magnetic field creates a changing electric field and vice versa. This implies that changing E and B fields, so electric and magnetic fields, can self-propagate themselves. And that might feel like a bit of a stretch. It's meant to be. So this implies that the changing E and B fields can self-propagate themselves. So the idea is if one changing field can create another changing field, and then that, say, the changing magnetic field creates a changing electric field, now that changing electric field creates a new changing magnetic field, that changing magnetic field creates a new changing electric field, and so on. That chain reaction is the self-propagation I'm referring to. And that idea, that self-propagation of changing electric fields and changing magnetic fields, is light. So light is the self-propagation of changing E and B fields. So that's precisely what light is. Light has a speed that is independent of its frequency and wavelength. Okay? So light has a speed that is independent of its frequency or wavelength. Okay, so obviously there's a bit to unpack in that statement, or at least there's an assumption, and that is that we are thinking of light as a wave, because otherwise it wouldn't have a frequency and wavelength. And so absolutely, light is a wave. We'll talk more about something called the duality of light, but for now we just want to think of light as a wave, okay? With, just like sound waves, frequency and wavelength. But the important thing is that the speed is independent of those two, okay? All right, so that, in fact, that statement about light is one of the big consequences of Maxwell's laws. Okay, so we can really say that that independence of its speed and that constant value of its speed follows directly from Maxwell's laws. Again, we won't prove that, but I want you to know that that is in fact the case. The last thing I'll say about the electromagnetic spectrum, which we would say is light. Right, another way of thinking about it. But here, let's make this like that. All right, so you can think of those two terms as interchangeable. EM spectrum or light, we mean the same thing. Okay, so what I do want to point out is that because of that independence, because the speed is independent, it means that as the wavelength goes up, the frequency must go down. And that creates this spectrum part. Because that way, if you know the wavelength of a particular type of light, a color of light or type of light, then you automatically know its frequency because the value of speed is constant. So we can say, thus, a spectrum of types of light is formed where frequency implies wavelength and vice versa. Okay, so let's get down into our equations. Okay, so the first equation is showing the speed of light, which we represent by the letter C. Okay, so this is the speed of light. Okay, I don't know why it's represented by C, but that is always a letter that we will use, a lowercase c, for the speed of light. So here we see that the speed of light has a value that is precisely 1 over the square root of the permeability constant times the permittivity constant. And again, the permeability constants and permeability and permittivity constants are these experimentally determined constants that came up when we were measuring the strength of the electric field and the magnetic field, respectively. Okay, so these are the constants that scientists have kind of found out their fine-tuned nature, found out what their values are experimentally, empirically. And now we know that, in fact, these two constants come together to give us one overarching constant, which is the speed of light. Okay, so the speed of light is one of the big constants of the universe. And again, indeed, it kind of defines, what the very properties of the entire cosmos, from the Big Bang down to, the smallest subatomic particles. So, what is that value? Okay. Well, if we think about the speed of light, then we can state a value here, and it's 3.00. But let's make sure I get a good value in here. But it should definitely round to 3.00. I just want to confirm that. Okay, yeah, because it's going to be 2.99, but we're doing 3 sig figs. If we're doing 4 sig figs, it would round to 2.998. So we'll go ahead and use that as our working value. Okay, so let's do that. So 2.998, but of course it's not 2.998 meters per second. We need an order of magnitude as well. And that order of magnitude is times 10 to the 8 meters per second. So a good way to put that, or to say it, is to say that it's about 300 million meters per second, because 10 to the 8 is 100 million. So 300 million meters per second is the speed of light. Okay, that's also 300,000 kilometers per second, another common way to express it. All right. And so that another way to think about it, besides just being defined by the two constants, permeability and permittivity, we can also think about the speed of light As also, quick note, these constants their values are included in previous lectures and in the formula sheet as well. So these, we can also think about it as a ratio of the strength of the electric field over the strength of the magnetic field. This means if you know the strength of one of those fields, you can then automatically find the strength of the other. And we'll see an example like that. Okay, so now onto another concept. If we're going to be talking about light and we're talking about a wave, it makes sense to talk about intensity. Now, if you took Physics 35 with me, then you saw intensity already. You saw intensity for sound waves, as well as just mechanical waves in general. We talked about the intensity of, for example, earthquake waves, but certainly the intensity of sound waves and their relationship to decibels. We won't be talking about decibels because that is unique to sound. But we still have the concept of intensity, okay? And it's still represented by uppercase I. Quick kind of interesting note here. Now we got uppercase I, intensity. Obviously, there's also current, which is uppercase I. And we have the moment of inertia, which is also uppercase I. So it's good to kind of keep track of which is which. Obviously, we could have a situation where those different values show up in the same problem, but a subscript should deal with it. Okay, so in any way, intensity represented here. All right, so it ends up being the electric field strength, the maximum electric field strength, times the magnetic field strength, divided by 2 multiplied by the permeability constant. Okay, so that's the physical manifestation of the intensity of light. So essentially what this is telling us is that, again, if I told you, for example, the electric field strength, and then you were able to, based on the constant, the universal constant, the speed of light, find the magnetic field strength, then you could go on to find the intensity of that wave. Okay? So for a particular field strength, or combination of field strengths, you will know the intensity of the light. Okay? Now, what are the units of intensity of light? Well, it's watts per square meter, so it's power per area. Good thing to remember. So watts per square meter. All right, so power per area. So it's basically energy per time per area is what intensity represents. And then so a good reminder of that is I included these 2 formulas down here just to make sure we kind of remember what we're working with. These aren't unique to light, but again, whereas of course these ones are unique to light. The formula, the line above. But here we have the energy. Okay. And here we're representing the energy as potential energy. That's because this is sort of the potential energy of the light to mostly push on things. So it's a concept that we're going to be introducing here, is that light can, since it does have energy, it can impart momentum onto objects. Okay, but more on that in just a minute. So U represents energy. And then we've got the intensity showing up right here. We have I, okay, already labeled, it's the same I. And then we have area for A, okay, that would just be in square meters. And then we have change in time. All right, so elapsed time. Okay, so then essentially if I was then to solve for intensity, I would then find that it's energy per area per time, okay, as I said before. But here instead, we're solving for energy. We can also represent intensity as power. Okay, that's just power in watts. Okay, and of course that's energy in joules. And while I'm at it, area in square meters, as I said. And then we can take that power and then just divide it by the surface area of a sphere. That's that 4 pi squared, 4 pi r squared. Okay, so it's the surface area of a sphere. And the reason we would do that is because if we have a source of light, in this case, that's the wave we're interested in, then as that source spreads out in all 3 dimensions, it's going to have a wave front. It's going to have a spherically expanding front of energy that is the surface of a sphere. And so it would have area of 4 pi r squared. Okay. All right, so that's kind of a review of intensity and its relationship to power and energy. Our next formula down here is really the formula that encapsulates the whole idea of the electromagnetic spectrum. And that's simply saying that the speed of light is equal to wavelength times frequency. Okay. So that is wavelength. And that would be in meters. And then we have frequency, and that would be in inverse seconds or hertz, because they're the same thing. Okay, so this again is a formula we would have seen for sound. In that case, it would have been velocity equals lambda times f. The only thing that's really unique here for light is that it's a constant. As long as light is in a vacuum, and that's something we'll be talking about more, but as long as light is in a vacuum, it will always travel at the speed of 2.998 times 10 to the 8 meters per second. So in that case, again, as I said, if you know lambda, you know f. You just solve for it, right? You know one, you know the other, in other words. Okay, so last two formulas here. We've got these ones. Both of these are our momentum formulas. Okay, so P is momentum. Okay, as it was back in the mechanics chapters where we introduced it. The difference here is we're talking about the momentum imparted on an object by light. So if light is hitting an object and that object is absorbing the light, that's absorption, then the momentum imparted on the light is imparted on the object from the light is the energy of the light divided by the speed of light. If the object is reflecting the light, like something shiny, as opposed to something dark, which would be absorbing it, then that shiny object would have a momentum imparted on it from light equal to 2 times the energy of the light divided by c. And the reason it's double is the same reason that a water wheel that reverses the direction of water gets twice the force as compared to a water wheel that just makes the water stop. By forcing the light to turn around, you have a double change in momentum, thus a double amount of momentum imparted on the object. Of course, from Newton's third law, equal and opposite forces. Okay? All right, so this is, in practice, we really see these formulas show up for something called a solar sail. And that's the idea that you could get a surface and put it in space where there's light coming from, a star like our local sun, and you've got that light hitting that big surface. And although the energy of all the individual particles of light, more on the idea of particles of light in just a moment, but all those individual particles of light, they add up and they actually will impart a significant momentum on the sail, pushing it. Okay, light can push things. In practice, we don't notice that. We don't go outside and feel the sunlight pushing us because it's a tiny, tiny force. There's one other point where the actual pushing force of light is manifest, is noticeable. That would be something called optical tweezers, which shows up in biology and the study of proteins. And the idea is you can get lasers, and you can actually, because those lasers impart a force, you can actually then pull things apart with that tiny force. It can be done to kind of unravel proteins, pull proteins apart, look at their elastic properties at that tiny, tiny nano scale, all thanks to the momentum of light. Okay,